Determine the square roots of z equals 8 minus 6i. So the first thing we do is say 8 minus 6i equals p plus qi squared. So what we want to do, when we distribute p plus qi squared, we get p squared minus q squared plus 2pqi. So what we do is we take the real component, which is the 8. We set that equal to p squared minus q squared. We take the imaginary component, which is negative 6i, and we set that equal to 2pqi. Now we can solve for q. Because remember, when you're trying to solve an equation, you can only solve for one variable at a time. So rather than dealing with p and q, we want to get q alone. So in order to do that, we need to divide by everything that is not q. So 2pi. And I'm going to do that to both sides of this equation. 2pi. So the left side is really easy. The 2's cancel, the p's cancel, the i's cancel, and we're just left with q. On the right-hand side, the i's cancel, so we divide negative 6 by 2, and we get negative 3. But remember, the denominator is still p. So now I can take that value, steal it, and put it right inside my parentheses over here. So instead of using q, I substitute q with negative 3p. Now, for the next line of our equation, we're just going to clean this up. So p squared minus, because we have the minus right here in front. But now we square that negative 3, and negative 3 times negative 3 is positive 9. And remember, our denominator is p times p, which is p squared. Equals 8. Now, the only ugly thing about this equation really is that p squared in the denominator. That makes us work. So I'm going to distribute that denominator through the entire equation to make that p squared go away. My goal is to not have to deal with that p squared in the denominator. So I distribute everything through. So to start, we say p squared times p squared. We know our base is p, but we add the exponents. So 2 plus 2 is 2 to the 4th power. Remember, we're getting that 4 from adding the exponents. Next, the p squared makes this p squared cancel because p squared over p squared is just 1. So 1 times 9 is 9, so it's minus 9. Equals, and here's the detail people might forget, we're distributing p squared to everything, so we have to multiply it by the 8 as well. So we also get 8p squared on that side. Now, in order to make this factorable, what I need is everything on the same side of the equal sign. So I keep p to the 4th, but I bring over the negative 8p squared. So on this side, it becomes negative 8p squared. Minus 9 equals 0. And now I can think about factoring this trinomial. So when I go to factor, I have p squared with a plus, and I have p squared with a minus, because p to the fourth is a perfect square. So I just take the square root. P squared times p squared is how you get p to the fourth. And I know I have a 9 over here, so I know that my signs are different. So it's plus, minus. Now I think of factors of 9 that add up to negative 8. Since the signs are different, I know that the negative is bigger. So 9 goes with the negative, and 1 goes with the positive. Because 1 times negative 9 is negative 9. 1 plus negative 9 is negative 8. So it's the whole idea of factor sum equals 0. So when I want to factor this part of the equation for p, the one thing I want to point out is we are looking for the real number part, right? If my answer has an I in it, the I goes with the Q. So since the P is the real and Q is the imaginary, I want to make sure that my answers are real. And if you notice, P squared plus 1, because of this plus in the middle, will always give us an imaginary result. I can't factor that down and get a real number by itself because there's going to be the I involved. So I'm going to go directly to p squared minus 9 equals 0. And when I factor this is going to factor to p plus 3 times p minus 3 equals 0. So with p plus 3 equals 0, we actually subtract 3 from each side, and we get that p equals negative 3. So that's our first solution for p. Now, the other opportunity is p minus 3 equals 0. So if p minus 3 equals 0, this time we add 3 to both sides, and therefore p equals positive 3. And that's our second value of p. So now we've determined that p is either negative 3 or positive 3. So we're going to take these results and substitute to find q. So this negative 3, I want to know what is the value of q if p is negative 3. So q equals negative 3 divided by, and here we just substitute in negative 3 for p. Now, a negative over a negative is a positive. 3 over 3 is 1. So q equals 1. And that's the q that goes with negative 3. So now down here I want to consider if p is positive 3. So I use this same equation again. Q equals negative 3 over And this time, when I substitute p in, I have a positive 3. And negative doesn't cancel out, but 3 over 3 is 1. So in this situation, q equals negative 1. So when I put my answer in down here, notice that negative 3 goes with a positive 1. So this is an ordered pair. That negative 3 has to be with this output because when I put P in, this is what I get for Q. So Q equals 1. So now when P is positive 3, Q equals negative 1. And that's how we solve. So the only thing that's left for us to do is write this as a square root. So now the square root of z equals negative 3 plus 1i, or just I. The other square root of z equals positive 3 minus 1i. And that's how you calculate the complex roots. And that is our answer for question number 4.